All right, let's dive right in. What if I told you that a cornerstone of our digital world, the SHA 256 hash function, might not work the way we've always been taught? Today, we're going to unpack some really groundbreaking research that suggests a whole new way of looking at this cryptographic workhorse. And this isn't just a small tweak, folks. It's a potential shift in the entire paradigm. So, to really get our heads around this, we have to kind of reboot our whole concept of what a hash function even is. Forget everything you've heard about it being a random, one-way street for data. We're about to look at SHA 256 in a completely different light. Okay, so you know the conventional view, right? We've always pictured SH256 as this sort of information blender. You toss data in, it gets violently scrambled into something totally irreversible and random. The goal is maximum disorder, pure entropy. But this new geometric view, it flips that idea on its head. It says SH256 isn't a blender at all. It's more like a mechanical mold. It doesn't destroy information. It carefully folds it, preserving all that information in the form of a complex but ultimately predictable geometric shape. And this is where it gets really wild. The best analogy for this new theory comes from biology. The research suggests that the algorithm uses these mathematical forces. They even call them cryptographic hydrophobic forces that are almost exactly like the forces that cause a protein to fold into its very specific, very functional shape. Think about that. This isn't a random mess. It's a highly structured process, all governed by predictable rules. A protein folding hash function, it's a really compelling metaphor for sure. But is it just a nice story, or is there some hard evidence to back it up? Well, let's get into the math, because this is where the rubber really meets the road. So check this out. At the core of this whole discovery is a surprisingly simple algebraic trick, and it's hiding inside every single one of SHA 256's 64 rounds. You see here, you take the update equation for register A, and you subtract the one for register E. Now pay attention to that T1 term. T1 is the really complex, nonlinear part. It's supposed to be the secret sauce, the magic that makes everything random and unpredictable. But when you do the subtraction, poof, it just cancels out. It's gone. What's left is a predictable, linear relationship, an invariant between the internal states of the algorithm. This is the mathematical crack in the armor of what we all thought was pure, untouchable randomness. And listen, this isn't just some abstract idea on a whiteboard. As you can see right here, this invariant is a real, verifiable property of the code itself. This predictable little relationship is hiding in plain sight, right inside the algorithm that's supposed to be securing countless systems as we speak. It's the first real piece of evidence that SHA-256 acts less like a random shredder and more like a machine with predictable interlocking gears. Finding that mathematical crack was absolutely huge, but really, it was just the beginning. It was the key that let researchers build a tool to actually peer inside this machine and see how it works. So what they did was engineer something they call a probe. It's basically a virtual instrument they designed to listen for these geometric echoes of the original data as it gets folded and processed through all 64 rounds. They wanted to answer a simple question. Is the inside of this thing truly random noise, or does it actually remember the shape of what you put in? And the results were, well, they were stunning. Instead of the random static you'd expect from an information blender, the probe picked up clear, non-random signals deep inside the algorithm. This chart here shows those echoes literally emerging from the noise. It's a clear sign that structured information hangs around through the whole process. That mold really does leave its mark. Okay, finding this hidden structure is fascinating, but it all leads to the one question that really matters. The one you're probably all thinking right now. What in the world does this mean for the security of SHA-256? Let's just cut to the chase. Does this new geometric view mean that SHA-256, one of the foundational pillars of all modern cryptography, is fundamentally broken? Is it time to panic? To answer that, we have to understand a really, really crucial difference. And honestly, the best way to explain it is with a good old-fashioned lock-picking analogy. Did the researchers find a master key that can just pop open any hash instantly? Or did they find something more subtle, but maybe just as powerful? What they found is not a master key. It's a tension wrench. Now, a tension wrench can't open a lock by itself. What it does is apply pressure. It creates tension. And that tension gives the lockpicker critical feedback. It lets them feel when a pin is set correctly. It turns what would be a blind random guessing game into a guided, informed process. In other words, it tells you if you're getting hot or cold. Now, to be totally fair, the research community is a bit split on this. One paper makes the absolutely explosive claim that yes, complete and efficient reversal is possible. They're talking about the master key scenario. They claim an algorithm exists that can reverse any hash in polynomial time, which for our purposes today just means efficiently, like really efficiently.
But there's a more cautious, empirically grounded paper that says, hold on a second. It concludes that what's been built is a tension field. That's our tension wrench. It's an incredibly powerful tool that gives you that hot or cold feedback. But it is not a full reverse oracle. It guides your guesses. It doesn't just hand you the answer.
So, let's bring this all home. What's the bottom line here? How does this discovery fundamentally change the problem of trying to break a hash?
And this right here is the ultimate takeaway. No, SHA 256 hasn't been broken in the sense that a master key exists, but, and this is a really big but, the entire nature of attacking it has been fundamentally altered. The problem is no longer just a blind brute force search. It has shifted from guess and hope to a constrained, guided search, a guess under tension. The rules of the game have completely changed. And that leaves us with one last, kind of mind-bending thought to chew on. If an algorithm, something totally abstract that we created, can be shown to follow geometric laws that mimic processes in biology, well, what does that say about computation itself? What other physical laws might be hiding in plain sight deep inside our digital world?